Chapter 18 of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Heidi Preuss. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Commerford Martin. Chapter 18. The Electric Railway. Edison had no sooner designed his dynamo in 1879 than he adopted the same form of machine for use as a motor. The two are shown in the Scientific American of October 18, 1879, and are alike, except that the dynamo is vertical and the motor lies in a horizontal position, the article remarking, "Its construction differs but slightly from the electric generator." This was but an evidence of his early appreciation of the importance of electricity as a motive power. But it will probably surprise many people to know that he was the inventor of an electric motor before he perfected his incandescent lamp. His interest in the subject went back to his connection with General Lefferts in the first days of the revolution of the stock ticker. While Edison was carrying on his shop at Newark, New Jersey, there was considerable excitement in electrical circles over the Payne motor, in regard to the alleged performance of which Governor Cornell of New York and other wealthy capitalists were quite enthusiastic. Payne had a shop in Newark, and in one small room was the motor, weighing perhaps 600 pounds. It was of circular form, encased in iron, with the ends of several small magnets sticking through the floor. A pulley and belt, connected to a circular saw larger than the motor, permitted large logs of oak timber to be sawed with ease with the use of two small cells of battery. Edison's friend, General Lefferts, had become excited and was determined to invest a large sum of money in the motor company. But knowing Edison's intimate familiarity with all electrical subjects, he was wise enough to ask his young expert to go and see the motor with him. At an appointed hour Edison went to the office of the motor company, and found there the venerable Professor Morse, Governor Cornell, General Lefferts, and many others who had been invited to witness a performance of the motor. They all proceeded to the room where the motor was at work. Payne put a wire in the binding post of the battery, the motor started, and an assistant began sawing a heavy oak log. It worked beautiful, and so great was the power developed, apparently from the small battery, that Morse exclaimed, "I am thankful I have lived to see this day." But Edison kept a close watch on the motor. The results were so foreign to his experience that he knew there was a trick in it. He soon discovered it. While holding his hand on the frame of the motor, he noticed a tremble coincident with the exhaust of an engine across the alleyway, and he knew then that the power came from the engine by a belt under the floor, shifted on and off by a magnet, the other magnet being a blind. He whispered to the general to put his hand on the frame of the motor, watch the exhaust, and note the coincident tremor. The general did so, and in about 15 seconds he said, "Well, Edison, I must go now. This thing is a fraud." And thus he saved his money, although others not so shrewdly advised were easily persuaded to invest by such a demonstration. A few years later, in 1878, Edison went to Wyoming with a group of astronomers to test his taximeter during an eclipse of the sun, and saw the land white to harvest. He noticed the long hauls to market or elevator that the farmers had to make with their loads of grain at great expense, and conceived the idea that as ordinary steam railroad service was too costly, light electric railways might be constructed that could be operated automatically over simple tracks, the propelling motor being controlled at various points. Cheap to build and cheap to maintain, such roads would be a great boon to the newer farming regions of the West, where the highways were still of the crudest character, and where transportation was the gravest difficulty with which the settlers had to contend. The plan seems to have haunted him, and he no sooner worked out a generator and motor that, owing to their low internal resistance, could be operated efficiently, than he turned his hand to the practical trial of such a railroad, applicable to both the haulage of freight and the transportation of passengers. Early in 1880, when the tremendous rush of work involved in the invention of the incandescent lamp intermitted a little, he began the construction of a stretch of track close to the Menlo Park laboratory, and at the same time built an electric locomotive to operate over it. This is a fitting stage at which to review briefly what had been done in electric traction up to that date. There was absolutely no art, but there had been a number of sporadic and very interesting experiments made. The honor of the first attempt of any kind appears to rest with this country, and with Thomas Davenport, a self-trained blacksmith of Brandon, Vermont, who made a small model of a circular electric railway and cars in 1834, and exhibited it in the following year in Springfield, Boston, and other cities. Of course, he depended upon battery for current, but the fundamental idea was embodied of using the track for the circuit, one rail being positive and the other negative, and the motor being placed across or between them in multiple arc to receive the current. Such are also practically the methods of today. The little model was in good preservation up to the year 1900, when, being shipped to the Paris Exposition, it was lost, the steamer that carried it floundering in mid-ocean. The very broad patent taken out by this simple mechanic, so far ahead of his times, was the first one issued in America for an electric motor. Davenport was also the first man to apply electric power to the printing press in 1840. In his traction work he had a close second in Robert Davidson of Aberdeen, Scotland, who in 1839 operated both a lathe and a small locomotive with the motor he had invented. His was the credit of first actually carrying passengers, 2 at a time, over a rough plank road, while it is said that his was the first motor to be tried on real tracks, those of the Edinburgh-Glasgow road, making a speed of 4 miles an hour. The curse of this work, and of all that succeeded it for a score of years, was the necessity of depending upon chemical batteries for current, the machine usually being self-contained, and hauling the batteries along with itself, as in the case of the famous Page experiments in April 1851, when a speed of 19 miles an hour was attained on the line of the Washington and Baltimore road. To this unfruitful period belonged, however, the crude idea of taking the current from a stationary source of power by means of an overhead contact, which has found its practical evolution in the modern ubiquitous trolley. Although the patent for this, based on his caveat of 1879, was granted several years later than that to Stephen D. Field for the combination of an electric motor operated by means of a current from a stationary dynamo or source of electricity conducted through the rails. As a matter of fact, in 1856, and again in 1875, George F. Green, a jobbing machinist of Kalamazoo, Michigan, built small cars and tracks to which current was fed from a distant battery, enough energy being utilized to haul 100 pounds of freight or one passenger up and down a road 200 feet long. All the work prior to the development of the dynamo as a source of current was sporadic and spasmodic, and cannot be said to have left any trace on the art, though it offered many suggestions as to operative methods. The close of the same decade of the 19th century that saw the electric light brought to perfection saw also the realization in practice of all the hopes of 50 years as to electric traction. Both utilizations depended upon the supply of current, now cheaply obtainable from the dynamo. These arts were indeed twins, feeding at inexhaustible breasts. In 1879, at the Berlin Exhibition, the distinguished firm of Siemens, to whose ingenuity and enterprise electrical development owes so much, installed a road about 1/3 of a mile in length, over which the locomotive hauled a train of 3 small cars at a speed of about 18 miles an hour, carrying some 20 persons every trip. Current was fed from a dynamo to the motor through a central third rail, the 2 outer rails being joined together as the negative or return circuit. Primitive but essentially successful, this little road made a profound impression on the minds of many inventors and engineers, and marked the real beginning of the great new era, which has already seen electricity applied to the operation of main lines of trunk railways. But it is not to be supposed that on the part of the public there was any great amount of faith then discernible, and for some years the pioneers had great difficulty, especially in this country, in raising money for their early modest experiments. Of the general conditions at this moment, Frank J. Sprague says in an article in the Century magazine of July 1905 on the creation of the new art, Edison was perhaps nearer the verge of great electric railway possibilities than any other American. In the face of much adverse criticism, he had developed the essentials of the low internal resistance dynamo with high resistance field, and many of the essential features of multiple arc distribution, and in 1880 he built a small road at his laboratory at Menlo Park. On May 13th of the year named, this interesting road went into operation as the result of hard and hurried work of preparation during the spring months. The first track was about 1/3 of a mile in length, starting from the shops, following a country road, passing around a hill at the rear, and curving home, in the general form of the letter U. The rails were very light. Charles T. Hughes, who went with Edison in 1879 and was in charge of much of the work, states that they were second streetcar rails, insulated with tar, canvas paper, and things of that sort. Asphalt. They were spiked down on ordinary sleepers laid upon the natural grade, and the gauge was about 3 feet 6 inches. At one point the grade dropped some 60 feet in a distance of 300, and the curves were of recklessly short radius. The dynamos supplying current to the road were originally 2 of the standard size Z machines then being made at the laboratory, popularly known throughout the Edison ranks as long-waisted Mary Anns, and the circuits from these were carried out to the rails by underground conductors. They were not large, but 12 horsepower each, generating 75 amperes of current at 110 volts, so that not quite 25 horsepower of electrical energy was available for propulsion. The locomotive built while the rail bed was getting ready was a 4-wheeled iron truck, an ordinary flat dump car about 6 feet long and 4 feet wide, upon which was mounted a Z dynamo used as a motor, so that it had a capacity of about 12 horsepower. This machine was laid on its side, with the armature end coming out at the front of the locomotive, and the motive power was applied to the driving axle by a cumbersome series of friction pulleys. Each wheel of the locomotive had a metal rim and a center web of wood or papier mâché, and the current picked up by one set of wheels was carried through contact brushes and a brass hub to the motor, the circuit back to the track or the other rail being closed through the other wheels in a similar manner. The motor had its field magnet circuit in permanent connection as a shunt across the rails, protected by a crude bare copper wire safety catch. A switch in the armature circuit enabled the motorman to reverse the direction of travel by reversing the current flow through the armature coils. Things went fairly well for a time on that memorable Thursday afternoon, when all the laboratory force made high holiday and scrambled for a foothold on the locomotive for a trip. but the friction gearing was not equal to the sudden strain put upon it during one run and went to pieces. Some years later, also, Daft again tried friction gear in his historical experiments on the Manhattan Elevated Road, but the results were attended with no greater success. The next resort of Edison was to belts, the armature shafting belted to a countershaft on the locomotive frame, and the countershaft belted to a pulley on the car axle. The lever which threw the former friction gear into adjustment was made to operate an idler pulley for tightening the axle belt. When the motor was started, the armature was brought up to full revolution, and then the belt was tightened on the car axle, compelling motion of the locomotives. But the belts were liable to slip a great deal in the process, and the chafing of the belts charred them badly. If that did not happen, and if the belt was made taut suddenly, the armature burned out, which it did with disconcerting frequency. The next step was to use a number of resistance boxes in series with the armature, so that the locomotive could start with those in circuit, and then the motorman could bring it up to speed gradually by cutting one box out after the other. To stop the locomotive, the armature circuit was opened by the main switch, stopping the flow of current, and then brakes were applied by long levers. Matters generally, and the motors in particular, went much better, even if the locomotive was so freely festooned with resistance boxes, all of perceptible weight and occupying much of the limited space. These details show forcibly and typically the painful steps of advance that every inventor in this new field had to make in effort to reach not alone commercial practicability but mechanical feasibility. It was all empirical enough, but that was the only way open even to the highest talent. Smugglers landing laces and silks have been known to wind them around their bodies as being less ostentatious than carrying them in a trunk. Edison thought his resistance boxes an equally superfluous display, and therefore ingeniously wound some copper resistance wires around one of the legs of the motor field magnet, where it was out of the way, served as a useful extra field coil in starting up the motor, and dismissed most of the boxes back to the laboratory, a few being retained under the seat for chance emergencies. Like the boxes, this coil was in series with the armature, and subject to plugging in and out at will by the motorman. Thus equipped, the locomotive was found quite satisfactory, and long did yeoman service. It was given 3 cars to pull, one an open awning car with 2 park benches placed back to back, one a flat freight car, and one box car dubbed the Pullman, with which Edison illustrated a system of electric braking. Although work had been begun so early in the year, and the road had been operating since May, it was not until July that Edison executed any application for patents on his electromagnetic railway engine, or his ingenious braking system. Every inventor knows how largely his fate lies in the hands of a competent and alert patent attorney. In both the preparation and the prosecution of his case, Mr. Sprague is justified in observing in his Century article, "The paucity of controlling claims obtained in these early patents is remarkable." It is notorious that Edison did not then enjoy the skillful aid in safeguarding his ideas that he commended later. The daily newspapers and technical journals lost no time in bringing the road to public attention, and the New York Herald of June 25th was swift to suggest that here was the locomotive that would be most pleasing to the average New Yorker, whose head has ached with noise, whose eyes have been filled with dust, or whose clothes have been ruined by oil. A couple of days later, the Daily Graphic illustrated and described the road, and published a sketch of a 100-horsepower electric locomotive for the use of the Pennsylvania Railroad between Perth Amboy and Rahway. Visitors, of course, were numerous, including many curious, skeptical railroad managers, few, if any of whom, except Villard, could see the slightest use for the new motive power. There is perhaps some excuse for such indifference. No men in the world have more new inventions brought to them than railroad managers, and this was the rankest kind of novelty. It was not, indeed, until a year later, in May 1881, that the first regular road collecting fares was put in operation, a little stretch of 1½ miles from Berlin to Lichterfeld, with one miniature motor car. Edison was in reality doing some heavy electric railway engineering, his apparatus full of ideas, suggestions, prophecies, but to the operators of long-trunk lines it must have seemed utterly insignificant and excellent fooling. Speaking of this situation, Mr. Edison says, "One day Frank Thompson, the president of the Pennsylvania Railroad, came out to see the electric light and the electric railway in operation. The latter was then about a mile long. He rode on it. At that time I was getting out plans to make an electric locomotive of 300 horsepower with 6-foot drivers, with the idea of showing people that they could dispense with their steam locomotives. But Mr. Thompson made the objection that it was impractical and that it would be impossible to supplant steam. His great experience and standing threw a wet blanket on my hopes, but I thought he might perhaps be mistaken, as there had been many such instances on record. I continued to work on the plans, and about 3 years later I started to build the locomotive at the works at Gorik Street, and had it about finished when I was switched off on some other work. One of the reasons why I felt the electric railway to be eminently practical was that Henry Villard, the president of the Northern Pacific, said that one of the greatest things that could be done would be to build right-angle feeders to the wheat fields of Dakota, and bring in the wheat to the main lines, as the farmer then had to draw it from 40 to 80 miles. There was a point where it would not pay to raise it at all, and large areas of the country were thus of no value. I conceived the idea of building a very light railroad of narrow gauge, and had got all the data as to the winds on the plains, and found that it would be possible with very large windmills to supply enough power to drive those wheat trains. Among others who visited the little road at this juncture were persons interested in the Manhattan elevated system of New York, on which experiments were repeatedly tried later, but which was not destined to adopt a method so obviously well suited to all the conditions until after many successful demonstrations had been made on elevated roads elsewhere. It must be admitted that Mr. Edison was not very profoundly impressed with the desire entertained in that quarter to utilize any improvement, for he remarks, "When the elevated railroad in New York, up Sixth Avenue, was started, there was a great clamor about the noise, and injunctions were threatened. The management engaged me to make a report on the cause of the noise. I constructed an instrument that would record the sound, and set out to make a preliminary report, but I found that they never intended to do anything but let the people complain." It was upon the cooperation of Villard that Edison fell back, and an agreement was entered into between them on September 14, 1881, which provided that the latter would build 2½ miles of electric railway at Menlo Park, equipped with 3 cars, 2 locomotives, one for freight and one for passengers, capacity of latter 60 miles an hour, capacity freight engine 10 tons net freight, cost of handling a ton of freight per mile per horsepower to be less than ordinary locomotive. If experiments were successful, Villard to pay actual outlay in experiments, and to treat with the Light Company for the installation of at least 50 miles of electric railway in the wheat regions. Mr. Edison is authority for the statement that Mr. Villard advanced between $35,000 and $40,000, and that the work done was satisfactory, but it did not end at that time in any practical results, as the Northern Pacific went into the hands of a receiver, and Mr. Villard's ability to help was hopelessly crippled. The directors of the Edison Light Company could not be induced to have anything to do with the electric railway, and Mr. Insull states that the money advanced was treated by Mr. Edison as a personal loan and repaid to Mr. Villard, for whom he had a high admiration and a strong feeling of attachment. Mr. Insull says, "Among the financial men whose close personal friendship Edison enjoyed, I would mention Henry Villard, who I think had a higher appreciation of the possibilities of the Edison system than probably any other man of his time in Wall Street. He dropped out of the business at the time of the consolidation of the Thomson-Houston Company with the Edison General Electric Company. But from the earliest days of the business, when it was in its experimental period, when the Edison light and power system was but an idea, down to the day of his death, Henry Villard continued a strong supporter, not only with his influence but with his money. He was the first capitalist to back individually Edison's experiments in electric railways." In speaking of his relationship with Mr. Villard at this time, Edison says, "When Villard was all broken down and in a stupor caused by his disasters in connection with the Northern Pacific, Mrs. Villard sent for me to come and cheer him up. It was very difficult to rouse him from his despair and apathy, but I talked about the electric light to him and its development, and told him that it would help him win it all back and put him in his former position." Villard made his great rally. He made money out of the electric light, and he got back control of the Northern Pacific. Under no circumstances can a hustler be kept down. If he is only square, he is bound to get back on his feet. Villard has often been blamed and severely criticized, but he was not the only one to blame. His engineers had spent $20 million too much in building the road, and it was not his fault if he found himself short of money, and at that time unable to raise any more. Villard maintained his intelligent interest in electric railway development, with regard to which Edison remarks, "At one time Mr. Villard got the idea that he would run the mountain division of the Northern Pacific Railroad by electricity. He asked me if it could be done. I said certainly. It is too easy for me to undertake. Let someone else do it. He said, I want you to tackle the problem, and he insisted on it. So I got up a scheme of a third rail and shoe and erected it in my yard here in Orange. When I got it all ready, he had all his division engineers come to New York, and they came over here. I showed them my plans, and the unanimous decision of the engineers was that it was absolutely and utterly impracticable. That system is on the New York Central now, and was also used on the New Haven Road in its first work with electricity." At this point it may be well to cite some other statements of Edison as to kindred work, with which he has not usually been associated in the public mind. In the same manner, I had worked out for the Manhattan Elevated Railroad a system of electrical trains, and had the control of each car centered at one place, multiple control. This was afterward worked out and made practical by Frank Sprague. I got up a slot contact for street railways and have a patent on it, a sliding contact in a slot. Edward Lauterbach was connected with the Third Avenue Railroad in New York as counsel, and I told him he was making a horrible mistake putting in the cable. I told him to let the cable stand still and send the electricity through it, and he would not have to move hundreds of tons of metal all the time. He would rue the day when he put the cable in. It cannot be denied that the prophecy was fulfilled, for the cable was the beginning of the frightful financial collapse of the system, and was torn out in a few years to make way for the triumphant trolley in the slot. Incidental glimpses of his work are both amusing and interesting. Hughes, who was working on the experimental road with Mr. Edison, tells the following story. Villard sent J.C. Henderson, one of his mechanical engineers, to see the road when it was in operation, and we went down one day, Edison, Henderson, and I, and went on the locomotive. Edison ran it, and just after we started there was a trestle 60 feet long and 7 feet deep, and Edison put on all the power. When we went over it we must have been going 40 miles an hour, and I could see the perspiration come out on Henderson. After we got over the trestle and started on down the track, Henderson said, "When we go back, I will walk. If there is any more of that kind of running, I won't be in it myself." To the correspondence of Grosvenor P. Lowry we are indebted for a similar reminiscence, under the date of June 5, 1880. Goddard and I have spent a part of the day at Menlo, and all is glorious. I have ridden at 40 miles an hour on Mr. Edison's electric railway, and we ran off the track. I protested at the rate of speed over the sharp curves, designed to show the power of the engine, but Edison said they had done it often. Finally, when the last trip was to be taken, I said I did not like it, but would go along. The train jumped the track on a short curve, throwing Crusoe, who was driving the engine, with his face down in the dirt, and another man in a comical somersault through some underbrush. Edison was off in a minute, jumping and laughing, and declaring it was a most beautiful accident. Crusoe got up, his face bleeding, and a good deal shaken, and I shall never forget the expression of voice and face in which he said with some foreign accent, "Oh yes, perfectly safe." Fortunately no other hurts were suffered, and in a few minutes we had the train on the track and running again. All this rough and ready dealing with grades and curves was not mere horseplay, but had a serious purpose underlying it, every trip having its record as to some feature of defect or improvement. One particular set of experiments relating to such work was made on behalf of visitors from South America, and were doubtless the first tests of the kind made for that continent, where now many fine electric street and interurban railway systems are in operation. Mr. Edison himself supplies the following data. During the electric railway experiments at Menlo Park, we had a short spur of track up one of the steep gullies. The experiment came about in this way. Bogota, the capital of Colombia, is reached on muleback, or was, from Honda, on the headwaters of the Magdalena River. There were parties who wanted to know if transportation over the mule route could not be done by electricity. They said the grades were excessive, and it would cost too much to do it with steam locomotives, even if they could climb the grades. I said, "Well, it can't be much more than 45%. We will try that first. If it will do that, it will do anything else." I started at 45%. I got up an electric locomotive with a grip on the rail by which it went up the 45% grade. Then they said the curves were very short. I put the curves in. We started the locomotive with nobody on it, and got up to 20 miles an hour, taking those curves a very short radius. But it was weeks before we could prevent it from running off. We had to bank the tracks up to an angle of 30 degrees before we could turn the curve and stay on. These Spanish parties were perfectly satisfied we could put in an electric railway from Honda to Bogota successfully, and then they disappeared. I have never seen them since. As usual, I paid for the experiment. In the spring of 1883, the Electric Railway Company of America was incorporated in the state of New York, with a capital of $2 million, to develop the patents and inventions of Edison and Stephen D. Field, to the latter of whom the practical work of active development was confided, and in June of the same year an exhibit was made at the Chicago Railway Exposition, which attracted attention throughout the country, and did much to stimulate the growing interest in electric railway work. With the aid of Messrs. F. B. Ray, C. L. Healy, and C. O. Mayhew, A track and locomotive were constructed for the company by Mr. Field, and put in service in the gallery of the main exhibition building. The track curved sharply at either end, on a radius of 56 feet, and the length was about 1/3 of a mile. The locomotive, named the Judge, after Justice Field, an uncle of Stephen D. Field, took current from a central rail between the two outer rails that were the return circuit, the contact being a rubbing wire brush on each side of the third rail, answering the same purpose as the contact shoe of later date. The locomotive weighed 3 tons, was 12 feet long, 5 feet wide, and made a speed of 9 miles an hour with a trailer car for passengers. Starting on June 5th, when the exhibition closed on June 23rd, this tiny but typical railroad had operated for over 118 hours, had made over 446 miles, and had carried 26,805 passengers. After the exposition closed, the outfit was taken during the same year to the exposition at Louisville, Kentucky, where it was also successful, carrying a large number of passengers. It deserves note that at Chicago regular railway tickets were issued to paying passengers, the first ever employed on American electric railways. With this modest but brilliant demonstration, to which the illustrious name of Edison and Field were attached, began the outburst of excitement over electric railways, much like the eras of speculation and exploitation that attended only a few years earlier the introduction of the telephone and the electric light, but with such significant results that the capitalization of electric roads in America is now over $4 billion, or twice as much as that of the other two arts combined. There was a tremendous rush into the electric railway field after 1883, and an outburst of inventive activity that has rarely, if ever, been equaled. It is remarkable that, except Siemens, no European achieved fame in this early work, while from America the ideas and appliances of Edison, Van Poel, Sprague, Field, Daft, and Short have been carried and adopted all over the world. Mr. Edison was consulting electrician for the Electric Railway Company, but neither a director nor an executive officer. Just what the trouble was as to the internal management of the corporation it is hard to determine a quarter of a century later, but it was equipped with all the essential elements to dominate an art in which after its first efforts it remained practically supine and useless, while other interests forged ahead, and reaped both the profit and the glory. Dissensions arose between the representatives of the Field and Edison interests, and in April 1890 the railway company assigned its rights to the Edison patents to the Edison General Electric Company, recently formed by the consolidation of all the branches of the Edison light, power, and manufacturing industry under one management. The only patent rights remaining to the railway company were those under 3 Field patents, one of which, with controlling claims, was put in suit June 1890 against the Jamaica and Brooklyn Road Company, a customer of the Edison General Electric Company. This was, to say the least, a curious and anomalous situation. Voluminous records were made by both parties to the suit, and in the spring of 1894 the case was argued before the late Judge Townsend, who wrote a long opinion dismissing the bill of complaint. See footnote 15. Footnote 15. See 61, Federal Republic 655. The student will find therein a very complete and careful study of the early electric railway art. After this decision was rendered, the Electric Railway Company remained for several years in a moribund condition, and on the last day of 1896 its property was placed in the hands of a receiver. In February of 1897 the receiver sold the 3 Field patents to their original owner, and he in turn sold them to the Westinghouse Electric and Manufacturing Company. The Electric Railway Company then went into voluntary dissolution. a sad example of failure to seize the opportunity at the psychological moment, and on the part of the inventor to secure any adequate return for years of effort and struggle in founding one of the great arts. Neither of these men was squelched by such a calamitous result, but if there were not something of bitterness in their feelings as they survey what has come of their work, they would not be human. As a matter of fact, Edison retained a very lively interest in electric railway progress long after the pregnant days at Menlo Park, one of the best evidences of which is an article in the New York Electrical Engineer of November 18, 1891, which describes some important and original experiments in the direction of adapting electrical conditions to the larger cities. The overhead trolley had by this time begun its victorious career, but there was intense hostility displayed toward it in many places because of the inevitable increase in the number of overhead wires, which, carrying, as they did, a current of high voltage and large quantity, were regarded as a menace to life and property. Edison has always manifested a strong objection to overhead wires in cities, and urged placing them underground, and the outcry against the overhead deadly trolley met with his instant sympathy. His study of the problem brought him to the development of modern substation, although the twists that later evolutions have given the idea have left it scarcely recognizable. Mr. Villard, as president of the Edison General Electric Company, requested Mr. Edison, as electrician of the company, to devise a street railway system which should be applicable to the largest cities, where the use of the trolley would not be permitted, where the slot conduit system would not be used, and where, in general, the details of construction should be reduced to the simplest form. The limits imposed practically were such as to require that the system should not cost more than a cable road to install. Edison reverted to his ingenious lighting plan of years earlier, and thus settled on a method by which current should be conveyed from the power plant at high potential to motor generators placed below the ground in close proximity to the rails. These substations would convert the current received at a pressure of, say, 1,000 volts to one of 20 volts available between rail and rail, with a corresponding increase in the volume of the current. With the utilization of heavy currents at low voltage, it became necessary, of course, to devise apparatus which should be able to pick up with absolute certainty 1,000 amperes of current at this pressure through 2 inches of mud if necessary. With his wonted activity and fertility, Edison set about devising such a contact, and experimented with metal wheels under all conditions of speed and track conditions. It was several months before he could convey 100 amperes by means of such contacts, but he worked out at last a satisfactory device which was equal to the task. The next point was to secure a joint between contiguous rails, such as would permit of the passage of several thousand amperes without introducing undue resistance. This was also accomplished. Objections were naturally made to rails out in the open on the street surface, carrying large currents at potential of 20 volts. It was said that vehicles with iron wheels passing over the tracks and spanning the 2 rails would short-circuit the current, chew themselves up, and destroy the dynamos generating the current by choking all that tremendous amount of energy back into them. Edison tackled this objection squarely, and short-circuited his track with such a vehicle, but succeeded in getting only about 200 amperes through the wheels, the low voltage and the insulating properties of the axle grease being sufficient to account for such a result. An iron bar was also used, polished and with a man standing on it to ensure solid contact, but only 1,000 amperes passed through it, i.e., the amount required by a single car, and of course much less than the capacity of the generators able to operate a system of several hundred cars. Further interesting experiments showed that the expected large leakage of current from the rails in wet weather did not materialize. Edison found that under the worst conditions, with a wet and salted track, at a potential difference of 20 volts between the two rails, the extreme loss was only 2½ horsepower. In this respect, the phenomenon followed the same rules as that to which the telegraph wires were subject, namely, that the loss of insulation is greater in damp, murky weather when the insulators are covered with wet dust than during heavy rains when the insulators are thoroughly washed by the action of the water. In like manner, a heavy rainstorm cleaned the tracks from the accumulations due chiefly to the droppings of the horses, which otherwise served largely to increase the conductivity. Of course, in dry weather the loss of current was practically nothing, and under ordinary conditions, Edison held, his system was in respect to leakage and the problems of electrolytic attack of the current on adjacent pipes, etc., as fully insulated as the standard trolley network of the day. The cost of this system Mr. Edison placed at from $30,000 to $100,000 per mile of double track, in accordance with local conditions, and in this respect comparing very favorably with the cable systems, then so much in favor for heavy traffic. All the arguments that could be urged in support of this ingenious system are tenable and logical at the present moment. But the trolley had its way, except on a few lines where the conduit and shoe method was adopted, and in the intervening years the volume of traffic created and handled by electricity in centers of dense population has brought into existence the modern subway. But down to the moment of the preparation of this biography, Edison has retained an active interest in transportation problems, and his largest work has been that of reviving the use of the storage battery for streetcar purposes. At one time there were a number of storage battery lines and cars in operation in such cities as Washington, New York, Chicago, and Boston. But the cost of operation and maintenance were found to be inordinately high as compared with those of the direct supply methods, and the battery cars all disappeared. The need for them under any conditions remained, as for example in places in Greater New York, where overhead trolley wires are forbidden as objectionable, and where the ground is too wet or too often submerged to permit of the conduit with the slot. Some of the roads in Greater New York have been anxious to secure such cars, and as usual the most resourceful electrical engineer and inventor of his times has made the effort. A special experimental track has been laid at the Orange Laboratory, and a car equipped with the Edison storage battery and other devices has been put under severe and extended trial there and in New York. Menlo Park, in ruin and decay, affords no traces of the early Edison electric railway work, but the crude little locomotive built by Charles T. Hughes was rescued from destruction and has become the property of the Pratt Institute of Brooklyn, to whose thousands of electrical students it is a constant example and incentive. It was loaned in 1904 to the Association of Edison Illuminating Companies, and by it exhibited as part of the historical Edison collection at the St. Louis Exposition. End of chapter 18.